Boolean algebra is a very important tool in the analysis and design of digital circuits. It uses the Boolean logic, which is implemented by the digital gates. So we will be using the basic gates that we have discussed so far: AND, OR, NOT, NAND, NOR, exclusive OR, and exclusive NOR, to help us identify the various aspects of the Boolean algebra. Let's start with the fundamental laws. The fundamental laws are based on the three basic gates: OR gate or OR logic, AND gate or AND logic, and NOT gate or NOT logic. If you will OR any signal, any Boolean variable with a 0, your output is going to be that variable. So A or 0 is going to be A. If you will OR any value, any signal, any digital value with a 1, your output is going to be a 1. And here is the basics of this. So A could be only a 0 or a 1. A 0 or 0 is 0. A 1 or 0 is 1. So whatever you are with 0, you get back that value. Similarly, if A is 0, you OR it with 1, you get a 1. If A is 1 and you OR it with 1, you still get a 1. So that means that whenever you OR any signal with 1, your output is going to be 1. We can further go through this. So A or A is A, so 0 or 0 is 0, 1 or 1 is 1. And if you OR a signal with its complement, so A or A bar, your answer is always going to be 1. So if A is 0, A bar is going to be 1, and you OR them together, your output is going to be 1. If A is 1, your A bar is 0, your output is going to be 0. Similarly, we can write similar expressions for AND. So A and 0 is 0, and it makes sense because when A is 0 and 0, output is going to be 0. When A is 1 and it with 0, your output is going to be 0. A and 1, your output is going to be A, because if A is 0, 0 and 1, your output is going to be 0. A and A is going to be A, and A and A bar is going to be 0. So a signal with its complement is going to be 0. So if A is 0, A bar is 1, your output is going to be 0 because we are ANDing them together. If A is 1, A bar is 0, your output is still going to be a 0 because we are ANDing them together. The last one for NOT, the basic law: if you do the double inversion, if you have A bar and you invert it again, your output is going to be A. So if A is originally 0, you invert it once, your output is going to be logic 1. You invert it again, your output is going to be logic 0, and you get back to your original value. Let's look at the commutative laws. So commutative law says that A or B is equal to B or A. And if it is AND operator, A and B is equal to B and A. We can prove this using a truth table. In fact, one of the basic ways to prove any Boolean algebra or any Boolean equality is by using the truth tables. So let's prove A and B is equal to B and A. So I have A, B, two variables, and I am going to write my truth table first. So 0, 0, 0, 1, 1, 0, 1, 1. And here I will have A or B, B or A. So 0 or 0 is going to be 0. If B is 0 here, 0 or 0, A is 0 here, it is going to be 0. 0 or 1, your output is going to be 1. 1 or 0, output is going to be 1. 1 or 1, your output is going to be 1. Now B or A column. So B is 1 or 0, output is going to be 1. B is 0 or 1, output is going to be 1. B is 1, A is 1, your output is going to be 1. And these two columns, they are same. So that means the equality holds true. For associative law, we have, if we have operators that are ampersanded together, that are grouped together, we can use our associative law to change the grouping. So if A or B is grouped together and we OR it with C, our output is going to be the same as A OR and a group of B or C. Similarly, A and B as a group ANDed with C is the same as A and a group of B and C. You can again use truth table to prove this. The last set of laws is distributive laws, and this is where it gets a little bit tricky. So the first distributive law is actually what we are quite used to in regular algebra. So A and B or C is going to be A and B or A and C. This is very similar to regular algebra where A times B plus C gives us A times B plus A times C. However, the second version of this law is not present in the regular algebra. So if A are B and C, then it is equal to A are B and A are C. We can prove this identity using the truth table. Let's set up our truth table. I have 3 variables. That means I have 8 possible combinations. And the columns that I need to set up is for each of these quantities. So the first here, I want to find B and C. So B and C. Next, I want to find A, R, B and C. That is my left side of the equality. Then I will find A, R, B. And I will find A, R, C. And my right side of the equality, A, R, B and ARC. So the rows here, let's set it up. An easy way to set up the rows of a truth table is that you start with the leftmost column of the variables. So I will make first half of the rows 0. So for values of A, I will say 0, 0, 0, 0, and then the next half I will make 1. Then I'll go to the second left column and I will do half of that. So instead of 4 zeros and 4 ones, I will do 2 zeros and 2 ones, then again 2 zeros and 2 ones. For C, I will do half of that, so only 1 0 and a 1 1. So 0 1, 0 1, 0 1. Now B and C. B and C is these two columns here. My output will be 1 when both of these values are 1. So which happens only at this row here, row 4, and in the last row. Everywhere else I have at least 1 0. So that means that those rows will be zeros. Now I have to OR it with A. And since I am ORing it, that means my output will be 1 whenever there is at least 1 in the two columns. So on A column, first 4 rows are 0. On the B column, first 3 rows are 0 and then I have a 1. That means that fourth row is going to be a 1. In my second half of the rows, all A's are 1s. So I do not even look at my B and C. And the rest of the rows, the first 3 rows are going to be zeros. Similarly, A or B, whenever I have a 1 in those two columns, I will have a 1 on the output. So the B is 1 1 in row number 3 and 4, and column A is 1 for the rest of 4 rows. So that means except of the first 2 rows where I will have a 0, every other value is going to be a 1. Now ARC. For ARC, the very first value, both are 0. And then my third row is 0. So second row, my C value is 1. So I have a 1 and then I will have a 0. And after that, I have a 1 in at least one of the columns. Now I AND these two columns together, ARB and ARC. So first row is 0, second row is 0 because ARB is 0, third row is 0 because ARC is 0, and the rest of the rows I have 1s. And if you compare this column over here with this column, you see that they are exactly the same. So that means this equality holds true. Now there are quite a few of other useful identities as well, which are listed in the book, and I have copied it over here. A and B is equal to A. A and ARB is equal to A as well. We can prove these identities either using a truth table or using the fundamental laws. So let's prove 618. So 618 says that A and ARB as a group is equal to A. So I have A and ARB equals to A. So the left side over here, I can rewrite it as A and A using my distributive law over here are A and B, which gives me A, because A and A is A from my basic AND law over here, are A and B. I can rewrite this as A and 1 because of my another basic law here for the AND. A and 1 is equal to A, or A and B. Now I can use my distributive law on this again, kind of reverse way. So if you imagine over here I have A, and if you imagine C is equal to 1 here, then I can write it as A and 1 are B. So this is sort of reverse distribution that I just did, which gives me A and 1, because 1 or any variable is going to be 1. That is another basic law. So I am left with A, which is what I was trying to prove, that my left side is going to be equal to A. Other useful identities are given here in these equations as well. You should go through each of these and prove either using the basic truth table or using the basic laws. In the exam, you might be given a Boolean identity and asked to prove it. Let's prove one of the identities that is a little bit more complicated. This is identity 624. In this identity, we have A and B, or A and C, or B bar and C, equals A and B, or B bar and C. It seems that A and C has magically disappeared. So how did that happen? Let's start with our left hand side over here. So on the left side, if I introduce a term A and B, A and C, if I introduce and 1 to this, it shouldn't change anything at all. Now in the next step, I am going to replace that 1 with B or B bar. And we know that any variable with its complement will reduce to 1 if it is R together. And or B bar and C. Now if I assume this term over here is X, then I can use my distributive law on this. So this would become X and B, or X and B bar. So if I replace X back to its original value, this will reduce to A and B over here. So X and B will basically reduce to A and C and B, which I can rewrite as A and B and C, or X and B bar, and X is A and C, so I can write it A and B bar and C, or this last term over here which is going to be B bar and C. Now, if you look at these first two terms, I can apply my distributive law on this again. If I assume that A and B is X, then this here is X and 1 or X and C. So I can rewrite is A and B and 1 or C. Similarly over here I can write A or 1 and B bar and C. And we know that anything that is ORed with a 1 gives us a 1. So this here is reduced to A and B or B bar and C, which is my right side of the equality. Let's talk a little bit about De Morgan's law. De Morgan's law says that A or B whole bar, if there is an inversion of some expression, that will be converted into A bar and B bar. Similarly, if there is A and B whole bar, that will be reduced to A bar or B bar. So essentially your operator under the whole bar, if it is or, it gets converted into and, if it is and, it gets converted into or, and your bar, your inversion is broken up to the individual variables. We are given here a circuit and a Boolean expression. So my Boolean expression over here is A or B bar C whole bar. We can use De Morgan's law on this and then implement our circuit that is the result of that application. So let's get started with this. I have A or B and C bar whole bar. So the first I apply it to the whole bar. So I will get A bar. This or here gets converted into and I am left with B and C. This bar is this original bar and I get a second bar on it because of that whole bar broken up. And we know that double inversion results in the original variable, so we are left with A and B and C. Now if I need to implement this circuit, it's pretty straightforward. All I need is invert my A signal and then I can pass it through either a 3-input AND gate, that is one implementation. So I have a B here or C here. In my second implementation, I can use two AND gates. So I will use first AND gate to AND A not B, so A bar B. And in my second AND gate, I will add in C into this as well. So this here is going to be A bar and B and C. Same thing over here, A bar and B and C. Let's talk a little bit about combinational circuits. Now, all the examples that we have seen so far of the Boolean algebra, Boolean logic, and digital gates, these are used to combine what is known as combinational circuit or combinatorial circuit. A combinational circuit is a direct implementation of a Boolean expression like this over here. The second type of digital circuit, sequential circuits, we have to distinguish how they are different from the combinational circuits. So in combinational circuits, there is no synchronization of signals is happening. Whereas in sequential circuits, we have a clock that synchronizes all the signals that are going through our circuit. So in this case, you can see that signal C and D has to pass through 3 gates, a NOT, then AND, then OR. Whereas A and B pass through only 2 gates. If we assume that all these gates take the same amount of time for execution, that means that signal A and B will be available at the output earlier than the computation of these two paths through which my C and D are going. Which means that my output can change as my signals are propagating through the circuit. In case of sequential circuit, that doesn't happen. My output will become only when my clock edge shows up. Now, combinational circuits can be written in two forms. The first form is sum of products. Sum of products is this form over here. So I have C bar and D bar, or C and D, or A and B and D. So each of these terms is a product term because we are putting together that term with an AND. Whereas between the terms I have an or an sum. So it is called sum of products. The alternate to sum of products is product of sums. In this particular course, we are not going to cover product of sums because that just adds confusion to the discussion.